Hello, everybody. It's 6 o'clock. Welcome on May 1st, 2023 to the 92nd birthday of the Empire State Building, the opening day, which we're going to talk about in the short two-part lecture, or two lectures in two parts of a look back at a retrospective of this book that Don Friedman and I published together in framing essays for a really spectacular artifact that's in the collection of the Skyscraper Museum, the Starrett Notebook. The builders, the brothers Starrett Brothers and their partner Eken, were the builders of the Empire State Building, and they left a record of the construction, and we thought how appropriate to celebrate their brilliance as construction managers and as masterminds of project management on the birthday of the Empire State Building. And so we're going to do this in two parts, as we did in our essays in the book. And I'm going to introduce a kind of overview that looks at the design and the process of the Empire State Building and the creation from its kind of financing pro forma through very, very briefly the architectural design, the logic of the constraints on the design, but then especially the building process as one of the elements in the program of the creation of the Empire State Building. Because when William Lamb gave four reasons or four parts of the program that the architects needed to satisfy for the owners of the Empire State. One of them was to have the building finished by May 1st, 1931. And that extraordinary accomplishment is something that the Starrett Brothers and Eken managed in about 11 months. And I'll talk a little bit more about the framing, about how to think about the dates, because some people use 13 months and some people use 18 months. But any way you cut it, it's an extraordinary achievement to conceive, create, erect, and open the building in about the span of a year and a half. And last month, the very popular YouTube channel B1M did a program that was sponsored by some software managers for construction projects, projects much smaller than the Empire State Building, asking why can't we build the way that today as fast as they built the Empire State Building. And there are a lot of reasons to that, and Don Friedman is going to help to answer that. So I want to Don is going to slide into the chair next to me in a moment, and here he is, because I want to introduce him as my colleague and co-conspirator in so many of the projects here at the Skyscraper Museum. And as you see, the Empire State Building is, both dividing us and bringing us together here in our different disciplines of art history and structural engineering, because Don is a historian, but he is a practicing structural engineer and works especially on historic preservation projects. He has helped the Skyscraper Museum from its absolute first days, when he figured out how to engineer the hanging of the big 60-foot long and 9-foot high curtains, heavy canvas curtains that had printed on them the buildings of Lower Broadway, and we hung them from the ceiling at 44 Wall Street in a space that was donated to us. So Don pitched in from the very first moments of the museum, and I have relied on him all of these years, including for an exhibition that some of his work is being recycled in. As you can see around me, we're in transition in the gallery because we have just taken down today Residential Rising, and we're in the process of installing Skymarks Landmarks, which is a look at the buildings of New York that have been designated by the Landmarks Preservation Commission that in the Skyscraper Museum's opinion are legitimate skyscrapers, whether they were from the 1880s or from much more recently. Last skyscraper designated is the AT&T building, 550 Madison. So within that spectrum, if it was a skyscraper in its moment, we consider it for the exhibition. And part of the way that we could have an authoritative view on what was a skyscraper in the 1880s was because of Don's work and his book, which I recommend to you all, The Structure of Skyscrapers in America, 1871 to 1900. Don created a book, but an Excel sheet also that we were able to split into the New York buildings and then show 252 buildings that were 10 stories or taller in those bracketed dates. And we're in fact recycling that for this exhibition on landmarks. So Don is not just a part of the origin story, but he keeps becoming more and more useful when we either recycle his work or call on him to sit next to me for a program like this. So Don is a structural engineer. He has many books under his belt about historical building construction, and he will demonstrate his expertise in a moment. But right now, I'm going to go to the slides. And I would like to, the Empire State Building book that we collaborated on, you're seeing the cover of it here, and you see the back cover in a moment, where the topping out ceremony so shows some of the steel workers. And this is actually the press board color is the background sheet for the mounting of the photographs that you see here. And you're going to see a lot of photographs that were taken or that were commissioned by Starrett Brothers Eken to record the work. This is one of the most celebratory you see here. And they do have labels like the one you see here that we used for the back cover that says, I have to get closer to read it, constructed in 11 months, the 1,252-foot Empire State Building was a marvel of engineering, of modern engineering. More than 30, that the frame rose at the rate of more than a story a day. So we want to shed a little light on how that was done, and Don is going to do that in particular. But let me just retrieve a page from, I believe this is Avery's journal that was donated by the Empire State Building, now in the collection at Avery, of clippings from newspapers and magazines. This one from the New York Journal on, I think you can see, on May 2nd, 1931. And it's showing Al Smith and his grandchildren and all of the other dignitaries in the lobby of the Empire State Building, and then atop the observation deck looking around the city below from the top of the man-made world, as the caption says, from the summit of the world's tallest building. But the Empire State Building was not just the world's tallest building in 1931 when it opened, it was the largest in terms of its floor area. And I want to emphasize that point in a moment. So as a really quick overview, it'll probably be about 20 minutes that we look at some of, or just under, that we look at some of those details. We want to look at the building process and how this extraordinary construction management and speed of erection was made possible by the brilliant management talents of the Starrett Brothers and Eken. So a few of the individual small photographs that are in this book, still available. This is the 25th anniversary of this book. It's still in print by WW Norton. And you can see some of the pages, the typical pages that reproduce the typescript manuscript that was compiled by the Starrett Brothers and Eken office. And then the pages were illustrated with these small photographs. The museum also received from the Starrett family a notebook that had not just the 78 or so individual photographs in the notebook, but a scrapbook that contained over 500 photographs. And those we're going to use to illustrate even more detail of the work. So this is just a sample of some of those photographs in the original. And here's the typescript manuscript that is measuring, or that is recording, on a peak day of construction, when the most men were at work on the site, over 3,400 men every day during the summer of 1930. And you can see the way that a typical job diary day book would show how many workers by trades were working at what location in the building, and tally up the typical workforce that day. This is the first and the last page. I'll show you more later. The photographs or the portraits of the two Starrett brothers, if you can see my cursor, with Paul Starrett, the more senior brother. There are actually 5 Starrett brothers, and the younger one was William Starrett, Bill Starrett, that you see here. And here's Andrew Eken, and then Hunter, another one of the executives in the company. The 5 Starrett brothers were all in construction in the 19-teens and 20s in one form or another. Some were architects. And sometimes they competed with one another. Sometimes they got along and sometimes they didn't. Somebody really should write a book about the Starrett brothers. The notebook that stayed in the family and was donated to the Skyscraper Museum, you see a sample of the pages here from the mooring mast details. The title of it is Erection Views of the Empire State Building, and this is a black construction board in white ink, all hand lettered. Each of the photographs has an inventory number and a small caption, as they do in the notebook. On our website, we call it the Empire State Building Construction Book for internet search reason purposes, the construction book. And you can find that on our website here. I'll give you a minute to look at it, but if you look on our homepage and you scroll all the way down and look on the left, the link is there in order to see a page by page record of the scrapbook. And then you can pull out individual images. Now, we had a wonderful interface that you see one page of here, back from about 2004 forward, when the whole of the 2 notebook and scrapbooks were put together in a database that would pull thematically the individual photographs that were on that topic. That project was done in Flash, and it was brilliant for 20 years until the Flash was no longer supported by any of the browsers. So we are in the process of reconstructing this in an open source and more future-friendly interface. Not that 2 decades in the internet isn't a long time, but you can see some of the pages here, and always the most popular view of any of the historical photographs of construction are the iron workers, you know, the Sky Boys. Louis Hine immortalized the Sky Boy, Frenchie, riding the derrick in with just you know, kind of nothing but Imperium behind him. But the idea of the title of Hine's book, Men at Work, is something that is celebrated by that photographer, and not so much this one, although workers certainly appear throughout the notebook. It's really a record of the processes of the work that the builders are recording in their compilation. And you can see some of that here. Some of the photographs are beautifully composed, but they're not exactly the ones that have become immortalized by Louis Hine. But they're fantastically interesting, and that's what Don's going to take us into in his section of the talk. So we see a variety of those here, and we're going to see them in some detail. But I want to talk a little bit about the design of the Empire State and its efficiency of design for the purposes of an office building, but also efficiency and speed of construction. And so in this rendering, which was the kind of arrived at design, it was the K plan and a series of plans that unfolded that shaped the building slightly differently each time. You see the elevation drawing without the mooring mast, which was added later. This was design was finalized around late September, October of 1929. And the mooring mast wasn't conceived of and then added to the design until November. So the idea of adding another 200 feet through this ornamental top with the kind of pseudo-functional aspect of being a mooring mast for dirigibles. Never really worked, but nevertheless, it made a top, a finish to this building that gave it a silhouette in the sky and a kind of machine age majesty that that made it New York's signature skyscraper. So we see it here in its 86-story version as designed by the architects Shreve, Lamb, and Harmon. It's actually Richmond Shreve at the top, not Robert, as you see in this dedication book that actually got his name wrong, oddly enough. But Lamb in the middle is mostly the design architect, but it's Shreve we're going to talk about in a moment. But first, equally responsible for designs with the architects are the financiers, the builders, the clients in the deal of the Empire State Building. So we have the titans of industry, the DuPonts, and John Jacob Raskob, who really was the kind of representative that drove forward the project, the financial project of the Empire State Building. And then, of course, Al Smith, former governor of New York and presidential candidate. Raskob had been the campaign manager not campaign, but the finance manager for the presidential bid by Al Smith, where he was so roundly defeated by the rest of America and came back to New York and got the job of being the president of the Empire State Building Corporation, still working with his close friend and colleague, John Jacob Raskob. So we move quickly on to what were the forces that shaped the Empire State Building. And in the year before, the Empire State Building was a glimmer in the eye of the wealthy men and directors of the board of the enterprise of making the Empire State Building project. Richmond Shreve was part of a group of industry professionals that created this book called The Skyscraper, A Study of Its Economic Height. And as you can see on the cover is the New York building, because it's shaped by the zoning law of 1916 and a series of setbacks. And one of the pages from this book you see here, where the shape of a building expands to the maximum amount of allowable space with the restrictions of New York City zoning, cuts light wells in order to be able to make sure that natural daylight can penetrate and keep first class A office space available to everyone. But these horizontal cuts that you see going through these buildings measure the building at different heights that then have a comparable page that with calculations of the return on investment of the cost of building a building of these 63 stories and 71 stories, et cetera. And then, an anticipated amount of rents against which you could measure the cost and the return. And so if we just take this shape that we're seeing of a building, a theoretical building that Richmond Shreve was responsible for calculating and then having drawn, we see it looks very close to the Empire State Building's shape, which does shave off some of the additional spaces. And why did they do that? Well, we can see that in further series of drawings. What we'd like to call, this was another feature of the website, which will be returned soon, hopefully online, so that all aspects of the database can be queried and interacted with. But the tower of plans that you see over on the right show you at the different layers where the shaft begins to narrow and where the elevator banks fall away, so that the consistent perimeter around each one of those floor plans is never any deeper than 28 feet from the outside window to the interior corridor. And that was one of the 4 features of the program that William Lamb articulated in an article that he wrote about designing the Empire State Building. You can see that the building is flat topped here still because the economic height of the Empire State Building is, well, it's really 80 stories, and then they added another elevator shaft from 80 to 86. So if you go to the top of the Empire State Building Observatory today, you go to the 80th floor, and then you transfer to another set of elevators in order to get to the observation level. That's because the economic height of that building was 80 stories, but they wanted to add a little bit more in order to ensure its primacy as the world's tallest building. So if we look at the superimposition of the ground floor plan, and then as the shaft rises and begins to set back, you can see that the ground floor is gigantic for the Empire State Building. It's 200 feet on the cross streets between 33rd and 34th Street. And it's about 425 feet long on its cross streets. I'll interrupt that thought in order to show you this advertisement that emphasizes the importance of light and the quality of light. A full floor on the 21st floor, you're seeing is emphasizing windows all around, but you see that shape of the floor plan that we saw in the Tower of Plans. That's very different than the post-war behemoth buildings with their deep floor plates, like you're seeing here on the Sears Tower, now Willis Tower in Chicago, which was 225 feet on the side. So actually about you could get about two of these inside the Empire State Building's ground plan. So that, it's extraordinary to think that what became the world's tallest building, Sears, and arguably the largest with over about 4.5 million square feet of space, which is twice as much volume of space or floor area as the Empire State Building. It does so by going straight up rather than these series of setbacks on the street that make the Empire State Building and 20s building so distinctive. Now you have Don Friedman, who's going to be talking as soon as I let him have the floor. But we're going to see just a few more pages of the men responsible. Al Smith was back there. Here are some of the other executives from Starrett Brothers and Eken. And because Don is going to talk about the construction, I will just quickly regale you with these series from the notebook to show you how wonderful they are, and to urge you to go to the website in order to see them and study them yourselves. So Don is going to talk about the sequencing of the work and the prefabrication of the parts that you can see in these pages from the notebook. And just to keep clicking through quickly, the genius of the just-in-time delivery as materials were brought to the site because of the large floor plate on a light and narrow gauge rail that made moving those heavy slabs of limestone for the facade, which were nevertheless all prefabricated parts and could fit easily on from the inside of the building, and then just be finished with brick on the outside and with light scaffolding on the exterior, as you see in these really wonderful photographs. So here these are some of the pages of the notebook. To conclude with the thing that people usually focus on for the Empire State Building, world's tallest, the mooring mast, and which we see here in a drawing that shows you some of its detail, and basically about a 17-story equivalent. It brings the height of the building to what they call 102 stories. You can see it here under construction in its steel armature and almost finished as it is in the photograph behind us for the new show in 1931. You see it compared to the other skyscrapers in New York of the day and to the Eiffel Tower, but you're seeing on its skinny side on the east-west axis. It's much thicker, as you see it in the the marching up of the next world's tallest building. That is an ancient, near almost 20 years old, 15-year-old graphic that we created for the website. It shows you the Burj Khalifa more than twice as tall as the Empire State Building, but actually with less space. A little bit more area on, as you can see when we're measuring in the bar graphs, the upside down bar graphs that show you the amount of square feet, square meters inside of these super tall buildings. I'm going to get off the screen now, but you see the Empire State Building, the second to the last in lavender on the right-hand side of this of our graphic. And it's the Empire State Building that remains for us at the Skyscraper Museum. Well, for me personally, my favorite skyscraper, but a standard, a metric by which to measure what we consider other super talls. Because if you think of the 19th century measure of the world's tallest building, it's the Eiffel Tower, 1889. Of course, it's not a building with an interior. It's not a functional commercial property, although it made money. It was an observation deck. And the Empire State Building, of course, makes a great deal of money from its observation deck. So these are things that, celebrate the human aspiration to and the desire to be high in the sky, to look from an elevated position. But the Empire State Building was a business proposition. It was shaped by finance. It was constrained by the particulars of the zoning law and the constraints of the 1930s technology that Don's going to talk about some more. But it set a standard in its time for speed of erection that really couldn't be matched. Can't be matched today because we build differently. Couldn't be matched at the time because the Empire State Building was twice the size of any of its peers or non-peers, because the Chrysler Building and 40 Wall Street, the next two tallest buildings in New York, together didn't have as much floor space combined as the Empire State Building did. In the 1930s measure, 2.1 million square feet. So the Empire State Building was in every way an extraordinary design, a complex engineering project, a magnificent symbol of New York, and the end of an era brought short by the Depression. Of course, Rockefeller Center was added after. It wasn't the end of skyscrapers by any means, but it was the culmination of a moment. And so I'm going to conclude with that, and Don will have his own say, and we will have questions if you would like to pose them in the chat for either one of us, which we'll take a look at after I guess I stopped sharing this screen, and Don is going to go to his screens.
Okay, so I'm not entirely sure how I'm going to live up to the billing I just got, but I'm going to try. The title of my little talk here is based on the fact, as Carol and I have been discussing, it's hard to believe it's 25 years since we first looked at that notebook and started picking apart what's inside of it. I want to just, this image is in the notebook. It's taken from the construction site of the Empire State Building, and it's looking to the north and a little bit east. The Chrysler Building on the far right. The four tallest buildings you see here, Chrysler, five tallest. Chrysler Building with the Shannon Building directly in front of it. The two buildings are across the street from one another, and there was this moment where I think it was the first and fourth tallest buildings in the world were directly across the street from one another. Then going to the left, you've got the Lincoln Building on 42nd Street, 295 Madison here, and then the one that's sort of interesting in this is 500 Fifth Avenue is under construction on the left there. Also designed by Shreve, Lamb & Harmon, and it bears a lot of resemblance to the Empire State Building, except that because of its location at the corner of Fifth Avenue and 42nd Street, it had different zoning envelopes on its two major facades, and as a result, it's not symmetrical, which you can see here. It was allowed to be bigger on the 42nd Street side than on the Fifth Avenue side, and that's why it looks a little bit lopsided. Those five buildings I just pointed out, none of them were there 3 years before this photograph was taken, which gives you a sense of the intensity of the boom that was taking place at that time. The reason I'm starting with this is that the Empire State Building was not built from, it was built from scratch. It was not starting from scratch. It was constructed 40 years into the steel frame skyscraper era. And prior to that 40 years, there was another 20 years of experimentation with how to get to the steel frame skyscraper. Not that people knew that that's where they were going, but that is what they did, is they experimented, and by 1890 had figured out how to build a steel frame, and by 1900 had figured out how to build one that made sense. And by 1930, it was something that could be churned out. And you can see, these 5 big buildings in the photograph, plus the Empire State Building, all being constructed in a very short period of time. So what you have to think of the Empire State Building as being a part of a technological system that had been developed specifically to do this. Steel was being used for a lot of other things. Riveted steel was being used for a lot of other things. If you look at a steamship of that era, you're going to see riveted steel that looks a lot like this photograph right here. But the overall system of steel frame technology that was being used in the Empire State, and what you're seeing here is the lowest tier of columns directly above the foundations. This was developed and led to this building. And in some ways, because of the layoff of construction between the Great Depression and World War II, when people started building tall buildings again in the late 1940s, it was a somewhat different technology, because steel framing had moved ahead and curtain walls had moved ahead while nothing was getting built. So this is the culmination of an era of technology. And what you're seeing here, if you see all of those rivet heads on these columns, there's always a maximum size that you can roll a piece of steel based on the mill technology. And if you want a piece of steel bigger than that, you need to build it up. You need to combine smaller pieces of steel until you get the size you want. We still do that today, although we don't use rivets. So if you're building up a large column at the base of a building today, you would weld it or bolt it. So all of those rivets you're seeing here are combining smaller pieces of steel, plates, angles, channels, some wide flange shapes into these very big column sections at the base of a 1,000-foot tall building. And there's nothing unique about these columns other than their size. And that isn't really even all that unique. And if you step back a little bit and look at the site as a whole, something that you start to see is how incredibly regular the framing is. If you want to build a very big building very quickly, and that was, as Carol said, that was part of the program here, you don't want to be spending a lot of time thinking about what you have to do. You want things to become routine. And the framing in the Empire State Building is incredibly regular. They avoided anything that would be difficult to do in steel. So for example, if you look at the setbacks, our architects and engineers refer to bays, meaning the distance between 2 points, and for an engineer, it would be the distance between 2 lines of columns. The typical setbacks at the Empire State Building are a full bay. And by doing that, there are no columns that have to be transferred in the middle. There's no column coming down halfway between 2 others. They simply drop off entire bays at a time as the setbacks take place. And that's much simpler than having setbacks that are only half of a bay or a portion of a bay, where you have to, it's easy to do in steel framing, but it takes more time, and it means that there's more unique framing. If you look at the steel of the Empire State Building, and I think, they went to great lengths that every beam would be identical, every girder would be identical to the extent possible. It's not possible for them to be truly identical because of the nature of gravity, right? The building load, the gravity load is going down, even wind loads. The wind is blowing on the building, but the effect of the wind gets greater as you go down. So the columns and the wind bracing in the building have to be heavier at the bottom than they are at the top. Well, if the columns are bigger at the bottom than they are at the top, then the beams have to be slightly shorter where they come up to the column, because the column has literally gotten fatter at the 2nd floor than it is at the 10th floor than it is at the 70th floor. So the framing at each floor is very similar, but not perfectly identical. But within that constraint that reality exists and gravity pulls down, the floor framing was as absolutely regular as it could be made. And this is something that you'll see on most buildings to some degree. But at the Empire State Building, it was taken as far as it could go. The beam, there are literally hundreds of identical beams within the framing. And this is something that people understood, again, from 40 years of developing this technology. The wood plank that you're seeing here, mostly in the background, is the beginning of the formwork to build the concrete floor slabs, right? Steel frame does not give you a building, it gives you a very large jungle gym. You need to put in floor slabs. This is the wood, that's the wood deck, that's the wood formwork to build the concrete floor. And based on looking at the right-hand side of this photograph, we're still in the base of the building. We're at the 4th or 5th floor, most likely. And what you can sort of make out, you see the shadows around each beam. The formwork wraps around each beam so that each beam would be encased in concrete for fireproofing. This is the standard construction of the era. The floor slabs in the Empire State Building are pretty much identical to those in every other steel frame building built in the late 1920s and the 1930s. And by using the standard technology and not doing anything special where it didn't need to happen, you can speed things up. There is something I want to point out, and hopefully you can see the cursor. There's a double beam at the perimeter of the building. Right, here's a floor beam, there's a floor beam, and then there's another beam outboard of it at the very edge of the building. And that is part of where things get special. So if you want to build this very big building very quickly, you look at what are the bottlenecks in construction. And one of the bottlenecks was building all of that wood formwork for the floors, but there was, at that time, in 1930-31, there was no way around it. So it had to happen, they couldn't get rid of it. But something that is always an issue is, how do you build the facade? How do you build the non-structural curtain wall? And something that one of the problems is that they faced with this building is that it was being fast-tracked. The construction began before every last detail had been designed. And that's a problem in terms of the support for the curtain wall, because the architects may be tweaking the facade long after the interior design is done and the structural steel has been fabricated for the interior. The facade is not yet entirely figured out. That's the first problem. And the second problem is the standard support at the time was what's called a hung lintel. It was a series of steel angles attached to the perimeter beams of the building at each floor, and that support the masonry. But as I forget, one of the Starrett brothers complained in the notebook that they said that, you know, there's a lot of adjustment required for those angles, and a lot of adjustment means a lot of time, a lot of labor, a lot of person hours. So if you could get rid of that, you can speed up the facade. There are other ways the facade was sped up, and I will be talking about that in a few slides. But anyway, so that double beam at the perimeter, the exterior beam does not support the floors. It's there solely to support the facade. And that was done specifically to speed things up. Another way of looking at it is that they spent more money on steel in order to spend less money on coordinating the structure and the facade. And this is the kind of calculation that has to go into the combination of design and construction that you see here. Here is the beginning of the facade construction. And if you may have noticed in some of Carol's long distance pictures, and I think I may have one of those pictures later on, when you take a picture of the Empire State Building from a distance on a sunny day, there's usually a gleam somewhere in the building. And that is because the long mullions that frame out most of the windows are stainless steel. And that's what you see being erected here. These two fellows are working on putting that piece of stainless steel in place. It's easier to see it from the back, or actually from the front close up. Okay, so here you see the way that they began to build the exterior wall. Those stainless steel mullions are connected to that secondary exterior beam, the extra beam that they added. And that's just a nice steel-to-steel connection, the stainless steel mullion to the regular steel of that beam. Those mullions hold three different things. They hold limestone panels, they hold cast aluminum panels, and they hold the windows. And as you can see, there's a what a limestone panel being lowered into position here. There is a need for people to be outboard of the building. In this photograph, the man on the left is standing on the floor inside the building. The man on the right is sitting on a scaffold outside of the building. It's almost impossible to build a curtain wall and never go outside the building. But most of the work is taking place on the inside. As Carol mentioned, the exterior scaffold could be very light compared to the heavy scaffold needed for a brick curtain wall, as for example, you had at the Chrysler building. Why did they need to go so fast on the curtain wall? Because that was one of the big bottlenecks in building this building. The Empire State Building is only 20% taller than the Chrysler building, but it's almost twice the floor area and more than twice the facade area. So if the exterior wall was built of brick, as at Chrysler, it wouldn't have taken twice as long because you could add more masons, but it would have taken much longer than it actually took. That would not have been possible to meet the May 1st, 1931 deadline. So this system, which is really a predecessor to modern stick-built curtain walls in a lot of ways, it was the result. You put up the stainless steel mullions, which most of that work was done from inside. There was somebody on the outside guiding them into place, but bolting them into position was done from the inside. You lower the aluminum panels and the limestone panels and the windows into place. Again, somebody is needed on the outside to make it work, but most of the difficult work is happening on the inside. Here's the back of that system. So we have we see two of the stainless steel mullions, one on the right, one on the left. This is one of actually both of these are the cast aluminum panels. And you see that all of them have these hooks sticking out of the back, which seems a little bit strange. Structurally, the way this curtain wall works is that when the wind blows on the wall, the wind load on the window and on this aluminum panel get transferred to the mullions, which are the structure that spans from one floor to the next to carry wind load. The New York City Building Code required that an exterior wall have masonry for fireproofing more than anything else. So even though it was not necessary for structure, they always knew they were going to build brick behind here because it was required by code. Those hooks are to connect the metal and the limestone to the brick. You actually see the very beginning of the brick on the left here. The big change in curtain wall design after World War II was the elimination of that requirement for masonry at the exterior wall. Here you see again people working on the inside, and this fellow on the left appears to be a mason building the brick back up. So all of that work is happening from the inside, which is much faster. It's much easier to work on the floor of the building where you can spread your tools out, you can spread the masonry materials out. You're not constrained by load on a scaffold. You're not constrained by having to move the scaffold every time you want to do something. You can walk around freely. So it's much easier to build the backup masonry standing on the floor than it would be standing on the scaffold. You can only do that if what the exterior face of your masonry looks like doesn't matter. And in this case, it doesn't, because the brick isn't visible anywhere. Again, unlike the Chrysler building. Here you see the brick built up. That's a limestone panel on the left. Limestone here. There's an aluminum panel. And here's the brick being built up behind the limestone. So it's basically being built backwards in order to gain speed. And all of this brick and all of the exterior veneer materials are connected solely to that extra outboard beam. And therefore, it's being done independently of the floor construction. Here you see what it looks like going up. So we've got the bare steel frame up at the top. The steel frame was being constructed at a truly incredible rate. They maxed out at just about a floor per day, actually slightly over a floor per day, which is just a truly record-breaking speed for building steel frame. The concrete followed, and then somewhat slower, you have the curtain wall going up. So what you're seeing here is the mullions in place and the aluminum panels, and the windows haven't come in yet, and the limestone hasn't come in yet. If you look at you pull back and you look at the building from a distance, you start to see bands. So up at the top where it's dark, that's pure steel. Then you have where the concrete slabs have been poured, that's where you have that sort of gray appearance. When the vertical stripes come in, that's the mullions put in place. And then you have the mullions and the aluminum panels. And then lower down where it starts to look more or less as it does today, that's where the limestone has been put in place. What you can't see is behind that, the brick is following slower than everything else. So there's another band that you can't see behind, and that may very well be where this line of scaffold is. As Carol mentioned, and the thing that I think most people find the most remarkable about this whole thing, they built a narrow gauge railroad on each floor. No engines, but standard railroad technology, including switches, because that was the fastest way to get materials around. Most modern construction sites use a hoist outside of the building. The Empire State Building was constrained by its site. It faces streets on three sides, and when it was built, it faced neighboring buildings on the fourth side, which have since been removed. So there was no place to put a hoist without taking a lane or two out of the street. In theory, they could have built a hoist that went up through the lower, through the biggest portion of the building at the bottom 5 stories. But in those days, they didn't do that. They didn't cut holes in the building to run a hoist. So the materials hoists were temporary elevators inside the permanent elevator shafts. So materials came up that were trucked into the first floor, put at the same place elevators are now, into a temporary hoist, brought up to the floor. But then they have to go quite long distances. And we're talking about heavy materials. We're talking about brick. We're talking about the materials to make mortar, the materials to make concrete. They have to go 50 or 100 or 200 feet. It's much faster to use these little rail cars on this railroad. That is a plan. So just to explain this picture, the outer rectangle is the base of the building. This dashed line that's the typical floors. There are, I think, something like 30 or 35 of those floors, which are the most common size in the shaft of the building. And then this squared off oval is the rail line for a typical floor. And you can see it gets all the way from end to end of the typical floor. It very much reduces the distance that materials had to be moved by hand. So this is it's not unique, but it's pretty close solution to how do you get materials to where they need to go inside of a construction site. The last topic I want to talk about is a little harder to pin down, and it is simply organization. If you look here, you see, I think it's 6 separate cranes that are being used to erect steel. And what you're seeing here, those little things sticking up, that is the top of a column splice, the bottom of a column splice, waiting for the next shaft of column to come along. So this picture was taken when the building was 1 story tall, and the next line of columns was about to be erected. And again, that white, what looks like a floor that you're seeing, is the wood formwork for a concrete deck, the temporary wood formwork. And just as you see today, we have shanties on top of a sidewalk shed to provide temporary office space. Later on, that was moved inside the building when there was a building to move them inside of. When you have so many cranes, and there were actually more as the building got a little bit taller, there's an enormous amount of paperwork that goes into organizing this. A piece of steel comes to the site. Well, which crane is going to pick it and put it where it belongs? And we think of spreadsheets as a computer thing. They, of course, existed on paper. They weren't called spreadsheets, but they were the exact same thing. It was a big grid where you could lay out numbers. And there's what had happened in general contracting during that same period that people were developing the steel frame was that people developed the organizational system to keep track of every one of those thousands of pieces of steel, every one of the thousands of workers on site, and so on. So this photograph is sort of my shorthand for that. And then Carol showed one of these before. This is not the maximum day. This is a day with only 1,900 workers on site. But again, think about that every one of them had to be tracked, what they were working on, and more than anything else, avoiding bottlenecks. The way that you build such a large building so quickly is to say, well, where are we going to run into a bottleneck next? Where are we going to have not enough laborers, not enough material, and so on in advance? And that was the genius of what Starrett Brothers Eken did in the end. And I just want to say, as an engineer, people assume I deal with numbers all the time, and to some degree I do, but less than you might think. What jumped out at me here was the line that the insurance, the proportion of maintenance of equipment in the insurance was calculated at 8.516%. I never use 4 digits of accuracy in my calculations because there's just no point. It's remarkable to me that somebody felt that they had to be that accurate for $24. This is the degree of tracking everything, of organization that took place on this project. And I think that is it. So thank you for your attention, and Carol and I are now going to answer questions.
If you do have questions to put in the chat, I guess we will read them here. And in the meantime, looks like there are a few. We just have to be able to see them here. Oh, thank you. Someone loves the lecture and is gazing at the Empire State Building as he or she listens. And I wonder, in light of the new advanced safety codes for building skyscrapers, if the building has been adapted in the years since in its construction with new codes in mind. And forgive me if I missed it, but why the fast pace of construction required for construction? Thank you.
Why don't you take the second question first, and then I'll take the first question second. You take the why the fast pace.
Why the fast pace? Because time is money, right? In order to abbreviate a even longer talk that I could have given in the introduction, and one that I take up at some length in a book that I wrote called Form Follows Finance, which is kind of self-explanatory, although it's about many aspects of the calculation. And one that I'll read you that was written in description of Fortune magazine of the Empire State Building that I'd like to conclude the evening with. Money is advanced in a project for the construction, for the land, for the materials, for every aspect of the project. And the faster that you can turn that amount of cash into, or lending into revenue, the better off and more profitable your project will be. And that's in an ideal world, not in the beginning of the slide into America's Great Depression, which is what the Empire State Building and so many other projects suffered. But when they first conceived the Empire State Building, and this happened in a letter of August 1929 between Raskob and one of the other bankers Willis Friedman, who was going to lend money for the project. They had 2 sets of numbers. One was for a 50-story building, the other was for an 80-story building. And calculating the costs and then the prospective return of 50 against 80 stories, they decided to build the 80-story building instead. And that became the birth of the Empire State Building. But that was only about 18 months before a key date. And why May 1st? Because in New York, in this era and going back into the 19th century, there was something called moving day, and leases for commercial architecture, for office space, were signed on an annual basis. Seems crazy, but for the building to be delivered on May 1st. And if you were going to clearly miss that date, you would miss the competition to lease your space to other buildings. And so the May 1st deadline was an absolute. They had to beat that. And Starrett Brothers Eken knew that from the very beginning. And indeed, under budget and ahead of time was their mantra if they could make it, and they did with the Empire State Building. The building was really ready to be delivered in mid-April of 1931, and opening day with a finished lobby and unrented space in the upper floors was accomplished. The elevators were to take the dignitaries to the observation deck and to survey the horizon from there. So you take the first.
Okay. I just want to begin with a statement about codes. Every building code has in it a provision that an existing building that doesn't have a problem, in other words, that nothing's falling down, can continue to be occupied. So an old building that wouldn't meet the design provisions of current code still meets code because it meets that provision. So if somebody says a building doesn't meet code just because it's old, that's actually not true. It just meets a different portion of the code. That said, old steel frame buildings typically work very well under current code. By our standards, the gravity loads they use, the occupancy loads were a little bit too high, which is good. The allowable stress that they used for steel was too low, which is good. Their wind load is okay. It could be a little bit higher by current standards, but there has, to my knowledge, never been a problem with a wind-induced failure of an old steel frame building. So obviously, empirically, it's okay. The biggest change in terms of structure between the New York City Building Code in force at that time and the code today is that the old code doesn't have seismic loading. But if you look at the ability of the old steel frames to take wind loading and you compare it to modern seismic loading provisions, it's pretty good. So there's no need to upgrade the Empire State Building or any other old steel frame skyscraper for current code for structure. There may be a need to repair them if they've suffered from excessive weathering or not enough maintenance, but that's a whole different issue.
There seems to be a lot of fascination about the light rail, and I'm not sure that we know the answer to this, but what was it used floor after floor? Was it moved in successive floors?
It was moved in successive floors. They had something like 5 or 6 floors worth of rail. So there were, at any given time, there were 5 or 6 floors that had the rail to distribute materials for the facade mostly, but also for interior partitions. And then they would disassemble the lowest floor, move it up to the next floor where they were working.
Mm-hmm. The same person would like to know, was this concept used on any other buildings afterward? I think not, because no one had a floor plate as large as the Empire State.
I think there have been similar systems used for some non-skyscraper large buildings. Very, there are, building like the Pentagon or some modern suburban office campuses where you have buildings that are 600 or 800 feet long. I think people have used similar systems, but as far as I know, this is the only skyscraper it's been used in.
Mm-hmm. Do we know where the bricks were sourced and how many bricks were required?
Oh, it's many millions of bricks, and it was just common brick because none of it's visible. So wherever people were getting common brick in New York at that time.
I guess it's worth noting, I think they do say the number of is like 10 million
Yeah,
bricks or something. I believe they did count and that we would find the answer in the book.
Yes.
But it's notable when you look at the history of the skyscraper back in the popular periodicals of the day, like Scientific American was a popular technical periodical. How much a building weighed in terms of its material was one way that they measured it, not just the floor area that it enclosed, but the amount of materials. And when you think of Norman Foster would ask, how much does your building weigh? Or Bucky Fuller said, sir, how much does your building weigh? This was actually a common way of calculating the cost of building.
I think that's related to, so the other huge artificial objects of that era are steamships. And steamships got longer faster than skyscrapers got taller until the very late 20s. So the Titanic is over 800 feet long, and there were no 800 foot high buildings in existence at that time. So, and with ships, you always.
792 with the Woolworth building.
So with a ship, you always look at how much it weighs. And I think there may be some connection there. And because there was an endless series of illustrations where people would show you how big a ship was by standing it on end next to a building. And people were comparing those two objects.
Mm-hmm. So in the lightning round here, we have, was the interior of the building move-in ready at the time it was opened? No. And Empire State Building, like almost all skyscrapers in New York, was a speculative office building waiting to be rented to multiple tenants, not the headquarters of a company. That's true of really 95% of all commercial architecture of skyscrapers in New York. And it's only after the building is leased that they subdivide the space according to how much you've rented. So when and someone asked about the empty state building, of course, with the contraction of the economy and businesses either going bankrupt or diminish or reducing the amount of space they took, and with all the competition of other buildings, the Chrysler building, all the buildings around Wall Street being completed at about the same time in 1929 through about 1931, there was an enormous amount of new space made available at the same time that businesses were across the country, and especially in New York, were contracting. So the nickname Empty State Building, which applied to the lack of rented space, only about a third was rented, about 2/3 remained vacant until the end of the Depression and really beginning of World War I. The building didn't become profitable until 1950, and it was the observation deck revenues that kept them anywhere close to being in the black for all of those first 15 years or so. But it was common not to finish space with the subdivision of space into offices and then to offer that to tenants. It was only finished after it was rented. Do you want to add anything to that?
No. It sounds good.
So appropriately, it's been called to our attention that May 1st is also International Labor Day, and questions about here, for example, what was the differential? Oh, wait, excuse me. This is finding the one about labor. May take me a second. Here's the other one. Thank you for praising the speed and skill of construction workers. For example, how fast they put up the steel frame, especially on May 1st today, which is International Labor Day. Can you tell us a little bit about the economics of the Empire State Building? I think we just did that. And for example, what percentage of the construction cost went to wages if the workers, and what percentage for the cost of materials?
I don't know the percentages. Something I can say as a sort of general comment is that, or two general comments. The first one is that people have been trying to reduce the cost of labor in construction. In the era I've studied, which is the 19th and 20th centuries, it was always how do we pay less for labor? The other thing is that over time, labor has become a larger percentage of the cost. Materials have gotten relatively less expensive over time, and labor has gotten relatively more expensive. And that's not really due to unionization, although that's a part of it. More than anything else, it's due to the fact that the price of materials has dropped, and the price of labor has, if anything, increased. So relatively, the price of labor at the Empire State would be less than it would be on an equivalent building today.
Do you know what percentage of columns were shop riveted?
They were all shop riveted. Again, so how do you accomplish two goals at once? How do you speed up construction, and how do you reduce the cost of labor? You don't want to do field riveting if you don't have to. Field riveting is more expensive than shop riveting in terms of labor, and it takes longer on site. If you think about a steel fabrication shop, you can have the same column, you can have 10 different rivets being installed at the same time in building up that column. So in terms of the columns, the only riveting that was done on site were the splices every 2 floors. In terms of the beam to column connections, that had to be done on site, of course, and the beam to beam connections. but anything that could be done in the shop was done in the shop, which is still true today. And back then they distinguished between field riveting and shop riveting, with field riveting being the more expensive, less desirable option. When I started work, it was typically shop welding and field bolting. Now we have shop welding and field welding, or shop bolting and field bolting. But it's always that same looking for how do you reduce the use of skilled labor on site, because that's more expensive than skilled labor in the shop.
We'll go for another maybe 3 or 4 minutes before we conclude. I know you know the answer to this one. How is lateral stability provided?
The Empire State Building is got diagonal bracing in the core around the elevators, and also moment connections in almost every frame in the building. So it's a huge moment frame that's stiffened with bracing at the core.
And here's a good nod to the engineers, so you can promote. What engineering discipline designed the steel beams?
Structural engineering.
But why don't you talk a little bit post and McCord and the profession of steel design and erection?
The structural engineer for the building was H.G. Balcom and Company, which they were a firm that did a lot of different buildings. They worked with Shreve, Lamb and Harmon, I think, fairly regularly. Homer Balcom is H.G. And they did the initial design. Then, as now, the portion of the connection design was done by the steel fabrication shop, which would provide drawings for review by the engineer of record. One of the things that happened here, because of the slowdown in the economy at the beginning of the Depression, and because of the size of the building, 2 different erection firms were used, alternating floors. And it was a way, if you think about it, it's a big building, there's a lot of connection work, and at that incredible pace of putting up a floor every single day, it would be very difficult for one shop, no matter how good their people were, to keep doing that. By breaking it to 2 firms, you got 2 days to build your one floor, even though the floor itself only went up in a day, and it gave the steel erectors a little bit of a breather. Because of that extreme regularity of the frame that I was talking about earlier, the connection design was standardized and is very much the same from one floor to the next, within the constraints of gravity and wind load, have bigger stresses at the bottom.
Well, so by way of concluding, because there are other questions, and the questions that I haven't selected for the live performance can all be answered in this book. As a matter of fact, I know that the answers are there. So I encourage you to buy and read the book by the Starrett Brothers as recorded, and then Don's essay, which illuminates at a greater length what we can offer here tonight. One of the perennial questions is how many people died on the during the construction, and Starrett Brothers Eken count 6 men who lost their lives. So let me just name them today in this summary of this building. So Giuseppe Tedeschi, L. De Domenichini, Reuben Brown, Sigus Anderson, Frank Sullivan, A. Carlson. They were laborers, an iron worker, and 3 carpenters. The Starrett Brothers trumpeted the safety of the site. And when we see the photographs of the workers today, we were horrified at how OSHA didn't exist at the time, and now they didn't wear hard hats or any kind of protection. All of those details can further be illustrated in the photographs, where you can enjoy those just for the imagery, but also the descriptions that we described. But one of the descriptions of the Empire State Building that, for me, is a perfect summary of not just the physical building, but the kind of metaphysical problem of creating a building in New York in this era. was summarized in a paragraph in Paper Spires, an article that appeared in Fortune magazine in 1930. And so it's a few lines long, but I'd like to read it for you by way of conclusion for this evening in this program. The writer says, these various elements fix the perimeter of an oddly shaped geometric solid, bounded on one side by 83,860 square feet of land, on the other by $35 million, on the other by the law of diminishing returns, on another by the laws of physics and the characteristics of structural steel, and on another by the conical exigencies of the zoning ordinances, and still another by May 1st, 1931. So on this May 1st, we thank you for joining us to celebrate the Empire State Building and its opening day anniversary. And we hope we'll see you next time at the Skyscraper Museum for more great construction history and celebration of New York buildings. And I will hold up the postcard for our coming attraction, the new exhibition, Skymarks Landmarks, where of course the Empire State Building is one of the featured treasures of New York. So join us next time and see the exhibition starting about a week from now. We're open Wednesdays through Saturdays from noon to 6, and we'd love to see you for Skymarks Landmarks. So thanks everybody for joining us. See you next time.